Chemistry. We're on to day 88. It's the second lesson in our review for the final exam in the last week of school. And we're going to just call this Additional Chemistry 2. We're going to deal primarily with the subject of titration. So titration is a laboratory process by which the known concentration of an acid is dripped into a base of unknown concentration. The purpose is to determine the concentration of the unknown base. The roles of the acid and base can be reversed. So it could be an acid of unknown concentration and it's being dripped into by a base of known concentration. The base of unknown concentration being analyzed is called the analyte. The acid of known concentration is called the titrant. The analyte, that's the base of unknown concentration being analyzed, resides in a flask. So you see the diagram over there on the right. The titrant, the acid of known concentration, is dripped in using a burette. That's the long glass tube that you see there. Acids and bases match up one molecule of acid to one molecule of base. So let's take a simple reaction between a strong acid, hydrochloric acid, and a strong base, sodium hydroxide. So what will happen is each of those molecules will go into water. They'll break up. The chlorine in the HCl and the sodium Na will just float off to the side and be spectators. They don't bond with anything else. And that leaves you with a hydronium ion from the HCl and H+, and a hydroxide ion from the strong base, OH-, and they get put together to form a water molecule, which is neutral, has a pH of 7. So that's the simple situation. So it's a 1-to-1. You have one molecule of acid neutralizing one molecule of base to form a water molecule, which is a neutral molecule. So reading below, one molecule of HCl neutralizes one molecule of NaOH to produce a water molecule and aqueous sodium ions and chloride ions. When enough titrant has been dripped into the analyte so that all of the acid and base have been neutralized, a chemical called an indicator suddenly changes color. How and why it does that is way beyond the scope of this course or even AP chemistry, but they have the ability to do that. They sense when the pH is neutral, or another thing they can do is sense that there's no longer any base in the analyte down in the flask, then they'll change color. Now that's a simple case. There's other things that indicators do. They can do it at different pHs, but in this case we're just taking the simplest case. So neutralization occurs when the number of moles of acid equals the number of moles of base. And when that happens, you just produce more water molecules, which are neutral. So let's take an example. Determine the concentration of a 20 milliliter sample of NaOH, sodium hydroxide, of unknown concentration, we don't know its concentration, in a flask by titrating 2 molar hydrochloric acid, that's the titrant, from a burette. So down below it shows what we know. We know the concentration of the hydrochloric acid in the burette. We don't yet know how much of it it's going to take to neutralize the base, the NaOH, down in the flask. So volume dripped is going to be determined. Now the unknown is the analyte. We know how much we put in the flask. We put 20 milliliters in. We don't know what its concentration is, and that's the purpose of the titration, is to determine the concentration of that unknown base. Okay, so let's see how we do this. It seems a little complicated at first, but it's really not too bad once you get used to doing it. So on the top, we're going to have an equation for the known titrant, and we're going to figure out how many moles of HCl we have. So the concentration, we said it was 2 molar, and that's how you write 2 molar, 2 moles HCl per liter of solution. So that's the concentration of the HCl we chose. We choose to use that concentration of HCl. And what we're trying to do down there at the bottom, that question mark, is the concentration of the unknown analyte NaOH. We want to know its concentration. So here's the way we do this. And there's concentration of NaOH we're trying to learn. So first we have to make a standard conversion simply because everything you do in a lab is done in milliliters. The burettes, the cylinders, everything is calibrated in milliliters, but molarity, as you see over there on the left, is calibrated in liters. So we have to use one of our 3 standard conversions. and the liters on the top cancel with the liters on the bottom. Now we have milliliters of solution. And now we're going to say that we had to drip 25 milliliters of solution before the color change. That is, before the solution neutralized. So that's something we didn't know at the beginning, but now we know that. That was our drip, drip, drip process, and we read off in the burette that it was 25 milliliters. So now we can calculate how many moles of HCl it took to neutralize the sodium hydroxide, the NaOH. And if you do the calculation on that, cancel your units, you get 0.05 moles of HCl were required to neutralize the NaOH. So the indicator changes color when the moles of HCl equals the moles of NaOH. Because remember, they match up one molecule to one molecule, 1 mole to 1 mole. This means that the solution is neutral. There's no hydronium ions, there's no hydroxide ions. So since we know it took 0.05 moles of HCl to neutralize, it must have neutralized 0.05 moles of NaOH. Again, it's a 1-to-1 relationship, so you have to have the same number of moles of each of those. And that tells you how many moles of NaOH you had. Now we're going to do the same equation on the top, except we're going to work backwards toward the question mark. So what was the volume of the NaOH that we said in the problem? We said it was 20 milliliters. That's how we knew that at the beginning. That's how much of the NaOH solution we put in the flask. Now we have to use the same liters milliliters conversion. There it is. And now if you do the math on that, and hopefully you know how to do the algebra on this problem, what you do is you get back to that question mark, and your final answer is 2.5 molar, 2.5 moles NaOH per liter of solution. So that's the concentration that we were trying to find out. That's what we didn't know that we wanted to find out, and we did. So it seems like a little bit of a complicated process, but I'm going to show you a shortcut way to do it. All right, it's a dilution problem. So here's the way you would do it. M1V1 equals M2V2. That's called the dilution formula. It's on your measures of concentration. Back when we were doing molarity and molality and parts per million and all that stuff, you had this equation on that measures of concentration sheet. So our M1 here is 2 molar. Our volume for the acid is 25 milliliters. Our M2 is what we're trying to find out, the molarity of the base. And the 20 milliliters is the volume of the base that we put in the flask. And if you just do the simple math on this, you come out with M2 equals 2.5 molar. So on the test, this is the formula you're going to use. You're not going to do everything I just showed you with all of those equations. You don't need to do that. You just do it this way. All right, let's move on. Okay, now we're going to move on to a subject called heating curves. Again, something that we just didn't cover in the class. It is covered in AP. So let's look at what's going on. It looks like kind of a busy graph here. You start in the lower left corner. You have some ice, and it's at negative 30 degrees centigrade. Now, the horizontal axis, you're adding heat. So what happens as you add heat? As you add heat, the temperature goes up in the ice. But as long as it stays below 0 degrees centigrade, it stays ice. That's the freezing point. Then when you get to 0 degrees, if you continue to add continue to add heat to the ice starts to melt. Now you notice something interesting happens at 0 degrees. As the ice is melting, its temperature remains at 0 degrees. It doesn't go up. So as long as ice is melting, the temperature is going to be 0 degrees centigrade. Once the ice is entirely melted, that means it's now entirely liquid water, then the temperature, as you continue to add heat, it continues to go up. That's that long sloped line in the middle. And the temperature will continue to go up from 0 degrees all the way to 100 degrees, which is the boiling point of water. Once water hits its boiling point, it can't go above 100 degrees. If you measure the temperature of boiling water, it should be 100 degrees. And the reason is because any molecules of water that have kinetic energy greater than 100 degrees is going to vaporize. It's going to go off as steam. So the temperature of the water will remain the same as long as water is boiling away into steam. Now, once all of the water is boiled away and all you have is steam, you can continue to increase the temperature of steam. Those are individual water molecules floating around in the atmosphere. And so that's that last sloped line that you see in the upper right side, and that's the temperature of the steam increasing above 100 degrees. Now, the only thing they want you to concern yourself with on the test is the melting, the one down there at 0 degrees. And they want to know, they're going to want to know the amount of heat required to melt a certain amount of ice, like, for example, 50 grams of ice. And so the formula is given there in the yellow boxes off to the left. Q equals moles. It's the number of moles of water that you have times the heat of fusion. And the heat of fusion is a fixed number for water, and it's 6.02 kilojoules per mole. So if you know how many moles of water you have, you simply multiply it by 6.02, and that'll tell you the heat in joules, or in kilojoules actually. Now, if they give you the amount of water or the amount of ice in grams, you're going to have to do a molar mass conversion from grams to moles. And it's 18.02 grams of H2O for every 1 mole of H2O. That's a number probably most of you have memorized by now. So you'll have to make that conversion first to get from grams to moles, and then you plug it into that formula. And we'll do a couple of practice problems on that. Entropy. Entropy is an increase in disorder in the universe for any spontaneous process. Without going too deep into the definition of spontaneous, it's simply a process that happens naturally. So, a broken wine glass has greater entropy disorder than a wine glass that is not broken. And let me take that example a little further. If the entropy is really great, then a reaction will become irreversible. You can't make it go backwards. So let's say you drop that wine glass and it broke into 2 very clean pieces. 2 pieces, both very clean. You could glue it back together. You could fix it. But if you drop that wine glass and it breaks into 100 pieces, there's no way you're going to be able to put that back together. The entropy is too great. The entropy change was too great, and you won't be able to piece that wine glass back together if it's in a lot of little pieces. And effectively, that question is going to come up on the test. So the symbol for entropy is capital S, and the units of measure for entropy is joules per Kelvin, but we're not going to get into that. So entropy means disorder, so it sometimes gets confusing. If you say something has greater entropy, it means it's more disorderly, not more orderly. So don't get that backwards. Greater entropy means greater disorder. Entropy is an increase in disorder for any spontaneous, any natural process. So dissolving an ionic compound such as KBr is a process that is both spontaneous, it happens naturally when you put it in water, and it increases entropy because ions are in a greater state of disorder. So clearly when you have that nice orderly crystal that you see in the image there on the left, that's greater order. When you put it in water and all of those ions break apart, that's greater disorder, so that's an increase in entropy. So the factors which affect standard entropy are, and I don't want to go through all these, but a couple of them, states of matter. Gases have greater entropy than liquids, and liquids greater entropy than solids. That's for kind of an obvious reason. Gases, the molecules are flying all over the place. In liquids, they can move. They're not perfectly aligned with each other, but they're still sticking together. And in solids, where they're stuck together tightly, that's greater order and therefore lower entropy. So gases have greater entropy, solids have lower entropy. Molar mass entropy increases as molar mass increases. Allotropes, I don't want to get into that one. Dissociation is the one we just saw. Sodium chloride dissolving in water produces sodium and chloride ions. And molecular complexity, I don't want to get into that one too much. So basically, if a reaction starts with a single reactant and breaks into a lot of different products, that would be an increase in entropy. It's like breaking the glass into a lot of different pieces. And you'll have a question like that on the test. Okay, Vesper. It's an interesting subject. We didn't have time to get into it. You will in AP Chem if you take AP Chem. So we're going to look at geometric shapes. So a methane molecule has a tetrahedral shape. And by the way, you can determine this shape from Lewis dot structures, from the Lewis dot structure of a methane, of CH4. We're not going to get into that discussion right now, but just understand that a methane is a tetrahedral molecule because it has four faces. Tetrahedron is a four-faced geometric shape. If you look at that thing, if you could put faces in between those outside atoms, they would have four sides, three around the side and one on the bottom. Now those white balls are hydrogens and the pink ball in the center is the carbon. So all the angles are perfectly even. They're all 109 degrees. All right, and that's a tetrahedral shape. Now, water molecules also have a tetrahedral shape, but with a difference. So let's go to the next slide. So here's a water molecule. The oxygen is the red ball in the middle, and the hydrogens are the two white balls on the outside. So that's H2O. Now, it also has four places where it could have hydrogen atoms, but it doesn't. It only has hydrogen atoms in two locations, the two at the bottom. You notice what's up on the top are two lone pair electrons, and we know we've done the diagram of water so many times, you should know that there's two lone pairs when you draw the diagram of water. So what do those electrons that don't have any protons attached to them do? They take that 109 bond angle that you saw from methane, from CH4, and they squeeze it down. They push down on the electrons that are bonding the hydrogen. So those two white lines between the oxygen and the hydrogen are actually electron pairs that are bonding. But what those lone pair electrons, the two pairs up at the top, do is they repel. That's why this whole thing is called valence shell electron pair repulsion. It's where the lone pair electrons repel the bonding electrons, the two pairs that are bonding the hydrogen, and they push them, they squeeze them downward. And so you notice that the angle is smaller. It's 104.5 between the two hydrogens, not 109 the way it was with methane, with CH4. And that's what happens when you have two lone pair electrons like that. It's going to push down on the bond angle and make the bond angle less. It's going to squeeze those two hydrogens closer together. And that's all you need to know about this for the test. Okay, finally, Coulombs Law. Coulombs Law states that the force between two charged particles is given by this equation. Q is the charge on each particle, so Q1 could be a proton, Q2 could be an electron, or the other way around, or it doesn't matter, they could both be protons. K is Coulomb's constant, we're not going to get into that. And D is the distance between the particles. So what you'll notice is if the particles are farther apart, then D increases. And therefore D squared increases by quite a bit. And since it's in the denominator of a fraction, it's going to make F smaller. Remember, if the denominator of a fraction gets bigger, then the number on the other side is going to get smaller because the distance gets greater, D squared. So let's pick an example. Let's say Q1 and Q2 are both 1. So it's 1 times 1 equals 1. Now, let's say the distance of a particular molecule, the distance is 1 whatever you want to call it, nanometer. Then that would be, and forget about K, we're going to ignore the K here. So it's 1 times 1 over 1 squared would be 1. Now, what if the distance between the two atoms in the molecule is 2? Then on top it would be 1 times 1 over 2 squared, which would be 4. So it would be 1 over 4. So the force would be weaker. Okay, as the distance between the particles gets farther, the force between them gets weaker. I think that's common sense. You feel the gravitational pull of the Earth because you're standing right on the Earth. You're very close to the Earth. You don't feel the gravitational pull of some star that's in the next galaxy because it's too far away. Even though it has a very great gravitational pull, greater than the Earth, you won't feel it because it's so far away. The distance from you is so great, so you don't feel its gravitational pull. So the bottom line here is that as the distance gets bigger, the force between the two particles gets smaller, it gets weaker. Okay, and that takes care of this lesson. The second and last lesson to prepare you for the final. We'll reinforce these concepts with a quiz game the next couple days after this lesson, and that'll take care of your lessons for this year.